Welcome. This talk was going to be a little experiment of my part with you. I'm trying to develop a deeper understanding on the concepts that we use in TOC to manage flows. And when I say manage flows, I'm trying to keep the definition of flows as open as possible. So what I'm trying to do here is to derive from the body of knowledge what are the inner principles we use to manage, understand and manage the flow effectively, and to test this, to see if I really did a good job. I established a criteria for myself, which is let's try to apply them, at least logically, whatever types of concepts I can understand. And these concepts should be viable and should be applicable to an area of knowledge that we never touched before with TOC. So I put myself to the challenge of finding an area, a flow, that we never managed with TOC, and seeing if the concepts I can come up with, the generalizations I can come up with, are compatible with this type of flow, if they're generic enough to handle a flow we never managed before. So this is the test I want to do with you, and use something that I think personally all of us have experienced in first-hand experience, which is traffic, actually traffic congestion and its effects on our lives. So let's try to test these generic principles and see what we can do with them. So let's start with the flow definition. Take a little look at logistical applications of TOC and what are the core clouds, what are the concepts behind them that will allow us to derive more generic concepts to manage any type of flow. Then I'll pick a different type of flow, traffic flow, and see what we can do with this type of flow. Then we're going to try to connect this back to other deeper principles that we use in TOC. The 5 focusing steps are these 3 basic flow management principles. And to compare these principles, I put these are logistical principles. Let's not confuse them with different and more profound principles like the 5 focusing steps or the 3 axioms on which TOC is based. They're a little bit above, but not as above as to be specific to one type of flow or another. So I'm trying to test them to see how generic they are. And then, well, compare them. How would we do to manage traffic under TOC principles? So that's the objective for today. So we start with, well, taking the 3 realizations Ellie Goldratt proposed in defining a flow. If you just look at the insights in operations, they will be there. They are put in many other places. That a flow has some common elements. First, there are always several elements that work together to achieve something. You're not just one-shot job. So you depend on something that came before, and probably somebody who comes after depends on you. And that's a flow. Otherwise, you wouldn't have a flow. Then reality is not so chaotic. There is some type of direction. Basically, you know what's behind and what's after you. But actually, flow is a very loose name. It could be like this sort of network, this mesh of things flowing around. It could have loops. But basically, you know in which direction things are going. That's OK. Reality is not that predictable. So if you put something in, you're not really expecting the outcome to be always the same. There is some degree of variability, chaos, but not so much. OK, so given this, we have several, but here we have 3 major applications of the 5 focusing steps and the TOC principles to different types of flows. I just picked 3 of the most important ones to see how they're managed and derive from them the generic principles, which is operations, basically something that outputs repetitively a certain group of products. The inputs are different from the outputs. There are some sort of transformations involved, and the touch time is significantly smaller than the lead time. So most of the time, things spend waiting in the flow. Then we have projects, single and multi-projects. It doesn't matter in this sense. The projects or outcomes are mostly unique, or at least in some small detail, they vary from another one. So they're not exactly the same to a larger degree of variability. And inputs are different from outputs. Also, we have transformation. But in this case, we cannot go right away and say, yeah, the touch time is very small compared to the total lead time. Sometimes it is, sometimes it's not. So we might have larger times really transforming things in the total lead time. And then we have distribution. Distribution is another simpler form of transformation. You basically move things around so that they will be ready when somebody needs them, at the place they need them, at the time they need them. Well, what do they have in common? If you were to look at them just critically, is there anything in common between the three TOC solutions? Distribution, operations, project management, something that we could derive and apply in other areas. And is there a way that we can use this answer to think of a uniform way to treat flow? Let's see. We could use two avenues. Go through the thinking process, look at the core clouds. I have 3 core clouds, great. I can use the 3-cloud approach and derive 1 core cloud and see if that can help me reconstruct the logic to other types of flows. And we can also take the accumulated experience, and still accumulating, it's changing pretty fast, but it's converging also pretty fast, implementation knowledge that's contained in the S&Ts, which is another way of looking at the same application. So I'll try to make a quick look at the two techniques and see if I can converge in the same principles, hopefully in the end, with the two techniques. So these are the 3 clouds. I have put here the clouds for operations, distribution, and project management in one single place. So basically, we're saying that we want to manage the flow well, which would be the generic view of all the 3 objectives of the clouds. If you take, for instance, the insights, you see the 3 core clouds. I'm just trying to generalize from them. It's a bit trickier with the projects cloud because the way it was written by Ali makes it flip very easily. So when you try to make the 3-cloud approach, you'll have a little bit of time understanding all the logic around it to see if C and D are not flipped, if D and D prime are not flipped as well in relationship with the others. But after a while, you can settle to an orientation that allows you to make a generic core cloud out of a conflict, how to manage a conflict. A flow. And then we have these 3 needs: constantly fight to increase flow, reduce cost, and do whatever it takes to meet endangered original commitment, which are basically telling us we need to protect the speed of the flow. The flow has to have certain basic speed of response. I need to know that something will come out. And it's the basic assumption that the flow will flow, otherwise it's not a flow. So I'm protecting this more conservative side of the flow. And then I have another aspect. I don't want only to produce one thing in the flow, even if it's fast. I need more things to go through. And these things are, at least, hopefully, in a large volume. So if I take the other need, constantly fight to reduce waste, protect sales, and don't jeopardize any other commitment, I'm trying to protect not the speed, but the volume that a flow produces. Then there are the actions that conflict in this area, which are release only what can be processed by the flow, basically it's choking the input, or the release, if we want to use more operational terms. Then release into the flow as much as possible to guarantee the volume. And that's a very generic cloud. We could see them in many types of applications we have. So what else can we do to find core concepts behind the flow management? We could use all the VVs we have now. We have 4 active, so to speak, templates and the viable vision initiatives. And these 4 templates all relate to some sort of operational improvement in order to achieve the viable vision. And if we take just this operational improvement, is there anything in common between the basic actions? And I'm taking just level 4 actions, not to be too detailed in that. So let's see. They touch SDBR, TOC distribution, CCPM, and TOC distribution. So they're covering basically the 3 applications. Let's see what we can see out of them. First, if we try to group the 4th level initiatives or actions in these templates, we see 3 basic groups. The first group, it's basically limiting or determining how much we'll put into the system. And these are the actions you find. choking the release, replenishing just to the consumption or to your target buffers, full kitting, planning, because in the planning you scatter and you spread the project, so you have this gating that Boaz was mentioning earlier. And you have internal pool distribution, ordering daily for suppliers. This is also some other mechanisms of restricting things from entering the flow. But that's not enough, because otherwise you will hit directly that core conflict, challenging the volume. You're just guaranteeing the speed, but then your flow may be full of holes and you cannot guarantee the volume. So you need other elements to complete the picture. So what are the other injections we can see? They're grouped in two other columns. The first column is basically getting the right things through. So that's priorities in the STBR environment and distribution and so forth. So the flow is not uniform. The elements in the flow are not always equal. So sometimes they get lost because of variability or other causes, and you need to reorder them or prioritize them, and this second group deals with that. And then there's a third group, which is very important. It's the group of improvement. You can take as much as you can from the flow, but there is a limit to that. Even with all the TOC tools we have, there's a moment when you exploit it very well, subordinated everything, you revealed a lot of capacity, and then you start using this capacity, eventually you run out of it. That's the whole basic of theory of constraints. There is always some constraint. You're not infinite capacity. So what do we do then? And the beauty of these three groups together is that they form a logical bridge that is needed in order to improve consistently, to form a PUGI. Because if you just try to go from group 1 to group 3, suppose that you never heard of TOC, you have some good ideas how to improve things, and then you jump to the elevating phase. Is there any simple and clear-cut way to prove to whomever is financing this improvement that you're really doing the needed things? That you already took everything out of the system that you should? And that's really worth their time or investment or whatever? That's tough. And the second group, interestingly, provides us with a key for any type of flow for you to prove how to implement the improvements in this flow. So let's explicitly define this and apply it to traffic management. And I'm not trying to put this back in these. Why? Because traffic management poses different questions for us. For instance, in all our applications, there's always a clear entry and exit point for the flow. Traffic management has no clear entry or exit point. So it poses interesting challenges. What is a buffer? How you measure it? How you manage by it? And other things like that. So if you can just try to follow logically through what will come out of it. Let's see. First, I'm trying to take the three groups I told you about and consolidate them in concepts. The first one deals with saturation. Something that's very common in many, many papers and studies, that a saturated flow does not flow well. You can take it from physics, from flow of fluids. You go from a laminar or a linear to a turbulent state. You can take it from operations management, queues theory, whatever. The more you go after a certain point, when the flow saturates, the least capacity there is to flow things through the system. The second thing is buffer management. Or in other words, you have to have a global view of management. How to prioritize things according to the overall objective of the flow, which is good speed and good amount of things going through. You need the two to accomplish the overall objective of flow. And then comes, well, how do I really improve it? Where, when, by how much? And you need some systematic way of answering these three questions. So, okay, how saturation works. It's true for most, if not all types of flow, that if you go up to a certain point, the flow becomes clogged. It doesn't matter what, it's distribution, you're eating up certain types of constraints, space, money. It's projects, multitask kicks in, you are basically go to a grind and halt if you put too much to people's minds, operations, and so forth. And the mechanism to flow slowing are basically connected to the interaction between the elements amongst themselves and to the resources managing the flow. We have some limited capacities of switching back and forth from one element to another, and sometimes the the objects themselves interact with each other and cause a slowdown in the flow. Then we have also another thing. When you saturate the flow, it creates waves. So if you create a wave, the wave is a very interesting thing because a part of the flow is going to be saturated, clogged, and around it you're going to find parts that they're starved. So you see people going with this strong preoccupation. Oh, if I choke the release, then I'll starve even more my system. That's not true. But they have this worry because they see waves of starvation and overwork and so forth passing through the systems when they are saturated. Then you have the deeper role of buffer management. Buffer management is not just a way to protect against variability. It's the key to understand how you can improve the system, as well as actively manage it, because otherwise it would just be a passive protection. It's much more than that. It provides us through two things, the guiding the execution priorities and guiding the process of ongoing improvement through the statistics of buffer, understanding where, when, and by how much I need to improve my flow. And it helps also saturation, because with the buffer, you're actually allocating some capacity to allow for variability in the speed that things cross the flow. So you're actually desaturating by separating certain capacity of the system to protect it against variability. That's the basic consequence out of having a buffer. And then inside that, you can even get more capacity knowing what are the priorities that you should assign to each element crossing the flow. So in this way, you can better utilize the capacity of the flow. So it has a double impact on the way the flow is being, well, operated. And then comes the guidance of execution. If you compare the rate of buffer consumptions and the relative progress of elements in the flow, which, if you like, is very well illustrated by the CCPM graph, amount of critical chain completed and amount of buffer penetrations we have. If you just analyze this ratio, you're going to see if the flow is progressing well or becoming more clogged or less clogged as time goes by. So what is real improvement? One that systematically brings the overall system closer to its goal. And for that, we need to define the goal and define a measure to see if we're really approaching this goal as time progresses. And the problem is the following. How can we answer this question? Each effort investment should yield quick and significant results, one after the other. How can we answer that? I have many good ideas being implemented in many areas. How can we say which ones in which order? And that's where the buffer management statistics, together with the evaluation of initiatives, is fundamental for us. So this is what we need. We need stability. We don't have too many resources to put into our growth, but we also need the growth. So the key to solve this and to keep these two together is know which initiatives will yield more value and which order we do them. So the three rules are basically capturing 3 steps of the 5 steps. We assume that we have a system where we can choose a strategic constraint. And as Ali told us some time now, we don't want to keep the strategic constraint flipping around all the way. So you choose some sort of guidance in your constraint, and then you fix it through your planning and manage it according to that. So that's the key for simplified drum buffer rope, for instance. Even if you have a bottleneck inside the house, you can still treat it as if the market is the only constraint, because you can protect also this bottleneck by your decisions on how to decide to exploit and how to subordinate all the systems to that. And looking over time, it's important to have something stable. For instance, the goal and how you measure it. Otherwise, you cannot really apply the 5 steps. Each time you change the goal, you have to revisit all your management orientation. Otherwise, you're going to be doing something that is not consistent with the system you're trying to manage. Well, let's apply this and see if they work for traffic management and what are the consequences we should expect if we were to implement this. First, what are the rules of traffic jams? Because traffic jams are really what stop us from really utilizing the capacity of traffic system. And well, you almost never see the start of it. And there are very good reasons for that. Well, sometimes you do. There's a car that broke down, a little accident, something interesting happening in the sideways, whatever. But after a while, you see interesting jams that have no reason for being. You're driving, you stop. You drive very slowly, then finally you start to drive off in a good speed, and there's no reason for that. What happened with this jam? Actually, in a big city, these are the most common type of jams that you encounter. Congestion does not have a clear reason for being. And then you have no clue why they keep on being like that, because you're in a normal 5-lane highway, have just this patch of high-density packed cars, and you've cleared that area, great, you're flowing, but what keeps it there? And then stop and go, get out of them without any warnings. They end abruptly. Why they happen? Why they persist? Well, the key for that is to understand the current solutions and the current things that people try to do in traffic management. They all are very concerned about regulating the entrance and the saturation of flow, which is the first principle. But they are still short of applying this in a wider scale. So for instance, you are in a normal high avenue in São Paulo by the side of the river. You have the fast lane, 5 lanes there, and you have the local street with 3 lanes and some entry points and exit points. When there is a lot of congestion, they usually close the entry points to try to limit the density of cars there, and in hopes to get the flow going better. But they just use this in this specific condition. The same thing goes for England and many experiments, Holland and many other places around. They just use it in point situations. They don't use it in a system-wide situation. Why don't they do it on a larger scale? Let's see, what's the goal of the system, and then check the 3 principles. The system is very simple. It's a transportation system. It has the following goal: allow people to be wherever they want, whenever they want, as much as they want now as well as in the future. How's that for a lofty goal? Okay, but then we have to measure it. It's never going to be attained 100%, but we need a simple measure, because if you don't have a simple measure, forget. Any initiative we'll do will be subject to subjective interpretations and political fights, and how we'll get this implemented in other areas, so forth and so forth. So we have to say the following: what is the time you lose actually trying to accomplish that goal in the transportation system? And the time spent, where is my time spent here? Well, the time spent in the process is a very good measure. If we try to see, okay, instantly I would like to be in that place, but I cannot. So I have to endure certain time in the traffic system. How long did I lose of my life? And assuming your life is restrained by 24 hours a day, you have a good constraint there. How much of the constraint you wasted in this process? Your personal constraint. So that's very interesting for the individual subjective transportation system as well. So what happens? Does this really make a difference, the saturation? I mean, we have, for instance, a car trying to make a lane switch. If he does, he'll create a compression wave here. A car trying to end with a compression wave here, he probably will have troubles entering, so he had to slow down to get in. So he's causing also another compression wave here. A car entering a ramp up, he will probably try to cause a congestion here, a little compression wave. If you are in a low density environment, that's not a big deal, but you have enough cars, this will turn into a congestion. And these are natural things. Cars are always switching lanes, entering and exiting points of highways. And what happens? If you have a congestion, other cars try to go away. So they create a congestion triangle that spreads around all the lanes. And what happens if you break down here? People stop here, they try to move around, they create other congestions that create other congestion that goes on forever until you clean up this little bottleneck. And what happens, for instance, if there is a bunch of cars here? They create a congestion wave in all the lanes. And this creates other lanes, other congestion waves that move forward. It's like waves in a pond. Okay, the water is not flowing with the waves, but the compressed group of molecules in the water is going that direction. So the traffic is exactly the same thing. So how can we see that in the models and the experiments in reality? They have this curve which measures the following. Here you have vehicle density per lane or per kilometer, it doesn't matter. How many vehicles are there in an area? The more vehicles you put in, there's this S-curve, inverted S-curve, that drops sharply after a certain point. This is the point of saturation. where the speed drops much faster than the amount of vehicles put into this place. So the speed is good in this area and then drops sharply here. This is a principle that everybody in traffic management knows, but now how to use it. How to go about it? Pinpointing CCRs. We have some CCRs in traffic. They're the recurrent points where the traffic always gets bad in certain hours of the day. Everybody in traffic management knows them by heart in their city, in their environment. The point is how you go about them. Should I choke the release where? To keep them from being saturated and the speed to be totally degraded. We should have them as simple as possible. For instance, you follow all the way from the point that is the CCR until the first place where you have like a lower density of vehicles, and there you choke it. Have many ways, many techniques that traffic guys use to choke it, from variable speed signs to really physically blocking a few lanes and other types of blockages that really limit the flow. What happened then? Then you increase the flow, the speed of flow through the bottleneck because you have lower density, and also you increase the flow of incoming cars in this part, so you will not create other congestions like this. What is the buffer? What's the buffer protecting us? It's protecting against variability. In the density, in the average speed, the flow of the streets change. This changes the density relatively in a specific point or another, so we need to handle this. So we need some empty space. This is the only thing that protects us in traffic against variability. If you're too close to another car, you're too dense. You don't have time to react. You don't have time to switch lanes, exit, or enter, or absorb the waves of congestion. A wave of congestion is totally dispersed by the enough empty space. But if you don't, it keeps on flowing and going back. So we have to revisit this. I mean, we have to know how much space we need in order to keep this flowing. Let's check it. How do we do it? We don't have like a specific place to put it, but we can measure the density and the speed of cars in several parts of the street or the roads. So using this, we can use this nice graph here, expand a little part of it, and see, yeah, in this part, the flow is still linear. We haven't got a turbulent state yet. It's not a chaotic environment. Here we can still manage to get the maximum out of how many lanes we have and what is the capacity of the system. So we can put a buffer here and say, how close are we to downgrading the speed? And it's easy to measure that because you can see the speed going down as density go up on each part that really presents a problem in your traffic system. So even if you don't know it a priori, it's very easy to gauge what is the range of density that is acceptable for each part of the traffic system. Because when you see the sharp drop, you know that's the end of the red. You're already saturating the system. And if you collect statistics of how much the traffic goes here after having some sort of limiting of the flow, of limiting of the saturation, then you can progress to the real improvement. What are the sources of invasions and things that throw you in the red or more after the red zone of the buffer? If you collect them systematically, then you can know where to place your improvement initiatives in a systematic way. And what is the way to measure them? It's how much time we save from people within the system. You can gauge that pretty easily. You can specialize that into types of transportation, types of vehicle, and so forth, and then evaluate which initiatives are better to do first and which initiatives to be done later on. Should I build a bridge or not, a deviation? And these initiatives have a strong problem because they also cause some sort of compression waves and they disrupt the traffic. So you need to take this in consideration as well. So all the principles, operational principles, not deep principles, but operational principles that allow us to manage flow boils down to three things. Control the saturation of elements in a flow. Be able to gauge globally and to protect these flow globally with buffer management. And using the statistics that you get from the buffer management in order to guide your improvement, your elevation or your initiatives to improve the system. The traffic management, they have a lot of good initiatives. You can pinpoint them everywhere. The English are famous for good ideas that do not progress well. They were the first to introduce the traffic sign that lets one car enter a highway per time. And that they did like, I don't know, 15 years ago or something like that. But that has been restricted to 20 miles of one piece of the ring of roads around London. And it stays there. Well, what about the rest of the ring? What about other roads? It's not that they don't have any problems with the congestion. They have a lot of problems, but they keep trying different things every day, and they don't settle, they don't finish the implementations, because they cannot bridge between the concept of saturation and improvement, because they don't have the concept of buffer, and they don't know how to concentrate their efforts in a systematic way. And the three principles are necessary to enable PUGI. You cannot do that without clearing up the system, without making good statistics with buffer management, and then guiding your initiatives. And it can and allows simple and quick results through focusing, because you clean up the system and you know what's preventing you from bettering it in the future. So this is what I had to share with you now.